Hey everybody, thanks for stopping by the shop again for another Screwy Tuesday. This is a follow-up to modifications. One little follow-up here in my own shop, and then we're going to go back over to Carl's. Carl read the comments, a lot of good feedback, and he'd like to respond and discuss it. And then along with that, we're going to just do a quick review of the machine also. So my modification here, I followed up. I told you I made tips for my spot welder here. And the way this one is set up is that the tips bolt on. So it had an Allen head cap screw going in to hold it into the copper rod. So I made little thumb screws out of copper. And so that will hold the tips on, and it's a nice little modification. I don't have to get a wrench out. I can just go ahead and put the tips on and off. So that's it here for my shop, and let's shoot over to Carl's. Thanks everybody for tuning in. So before we run to Carl's, I do have one other modification I just wanted to show you that I did in the shop here. So in a previous video, I showed you this digital microscope that I picked up from Banggood. They sponsor me, and I requested it and they sent it to me. And it does come with this stand, and it does work on the stand. It limits your height and things. And so from this stand, I ended up mounting it on this microscope base. Modified it so it could attach here. This would go up and down. The table would go up and down. Subsequent to that, I showed you mounting it on the Noga. Noga works great, got a lot of height adjustments and things. I just hated tying up my Noga most of the time. The microscope's not really going to be used that much in the shop, but it'd be handy. So it just happened, it dawned on me today that I have this height stand, and now I can raise the unit even higher than the Noga. I think I'm probably out of camera there. You can turn the camera, you can turn it any way you need to, and you still have the fine adjustment. And then what happened on the weekend, my wife gave me a little car for my grandson, and it had a stripped out screw, and I put it on the platform here, and of course it wouldn't work. It's too tall to actually fit in there. So this actually gives me a lot of flexibility so that you can actually put something very tall underneath the microscope. Or take it all the way down. So anyway, thought I'd just show you that, and now we're off to Carl's.
Okay, you guys really knocked yourselves out in answering my questions about what to do with this horizontal mill, and I really want to thank you, and my way of thanking you is to take all of your suggestions and doing a follow-up video, responding to most of the ideas and telling you what I really liked about them. So first of all, I want to go with Chris, Dale, and Silver Bullet and some others. You like the idea of overspeeding the spindles. Typically, the ideas was using a VFD and running it up to a 90 hertz or above, or replacing the 1750 RPM motor with a 3450. Good ideas. The problem is that this mill has two plain bearings. And plain bearings work really well at either low speed or high speed. They don't work terribly well for both low speed and high speed. They tend to be operating over a lower speed range than an equivalent ball or roller bearing. and they work the best when they're operated at one specific design speed. If they're operated slower than that design speed, they tend to go into what is called boundary layer lubrication, whereas there is some light metal-to-metal contact, and that increases the wear. If they're operated at quite a bit above their design speed, the fluid friction of the oil between the moving surfaces generates heat that expands the parts, and the shaft will tend to seize to the bearing, causing a seizure, and that also can destroy the surface of the bearings. So while a plain bearing can be designed for very high speeds, and to tell you about it, they're used a lot on cylindrical grinders running at high speeds. but that same bearing can't be used for a low speed. So for a milling machine where I want a higher speed range than the bearings were designed for, I don't think that's a good way to go. So no, I'm not going to change the motor. If we have time, I'll show you a little bit later some of the problems of changing the motor and how the spindle speed, how the spindle drive is arranged. And so, no, not going to change the motor, not going to install a VFD. Silver Bullet, you read my mind. This was my first thought, was to use a DA collet extension or possibly an ER with a 1/2 inch maximum collet capacity. Oh, there's a collet in there already. And bury the bearings back in the tool holder, something like this, to minimize the overhang. I don't want the tool to stick any farther forward than the 40 taper tool holders would normally provide. So this is my first idea, was how do I get something like this buried back inside there? So yes, Silver Bullet, I think you're onto something there. Jim, you suggested a speeder and found one on eBay for me. I like that idea, and it's probably the best of the ideas. That particular one has the problem, while it is a 40 taper on the drive end, on the driven end, on the drive end it's a drill press taper. I mean, a drill chuck taper. And I would rather have a collet, and that's why a collet sticking out here rather than a drill chuck taper. So I'll keep looking on eBay. Unfortunately, what I have looked at so far, the prices of those tend to be very close to what I paid for the entire mill. For a low-use accessory, I don't know, do I want to spend $300 to $500? I'm not entirely sure. There's another motivation for me, and I'll get to that in just a little bit. Eli, hello there, you old coot. I'm an old coot myself. You are quite right on your planetary gear set, and I have thought about that. Unfortunately, I always associate planetary gear sets with internal gears, and I really don't want to have to get into making one. I don't have one. I don't know much about internal gears. I've made external gears, and that gives rise to the thought, well, I can use what they call a reverted gear train, which for you guys that have South Bend lathes and things like that, that's known as a back gear drive. And I could do that with, just a second here, using a pair of square root of 3 gears. 20 tooth to 35 tooth is a possibility. So yes, a gear train built out into here somehow, held against rotation by something bolted back in here or up here, I think is a very, very likely possibility. Zephyr, you talked about using motorcycle headstock bearings. I had no idea that they were a steeper angle than the conventional Temkins. I like the idea. I'm not sure I follow what you're thinking on leaving the existing tapered bronze bushings in place and adding 2 more roller bearings. Take up a little space. I'll show you in the back. It's not an easy mount. And it would still, leaving the plain bronze bearings in place, I have the problem of overspeeding those. The mill could be changed to precision tapered bearings, but that would require mounting the body of the mill, the frame, on a large horizontal boring mill, reboring this. I would have problems because it's a gear drive onto the spindle. Oh boy, I just don't really want to go there. So no, I don't think, while it's interesting, I'm not sure that that would work too well. This brings me to Electric Gears, who really put out an effort for me. And I want all you guys who would like to take a look at what he's done, look at his drawings that he put on Imgur. All you have to do is go back to the previous video, look at the comments, and he has a link in there that will take you to what he's done. The only thing, basically what you did is what I'd like to do with this. The only thing that you did with it that has me concerned is that you have basically a a 40 taper tool holder sticking out about in here someplace. And that really takes up a lot of my distance here. I would like to have the collet about in this location rather than about in this location. That being said, I did spend a lot of time yesterday taking all of your drawings from MGUR, putting them into a Word document, printing it out so I can sit and study it in detail. I think I'm going to use your idea as a starting point for a possible external drive using a reverted or back gear. Let's call it a reverse back gear. Instead of going down in speed, I want to go up in speed. So I want to sum it up for you guys. I don't think overspeeding the existing spindle is a good idea because of the limitations on the bronze bushings. A speeder is probably the very best way to go. Just buy the damn thing and get it over with. Again, what I've seen so far is that the cost of those is very close to the cost of the mill. For a low-use accessory, I don't know. Besides, half the fun is solving the problem myself, and so that leaves a homebrew speeder of one kind or another using either a planetary or reverted gear set, or a high-speed spindle mounted out in here someplace using a separate drive motor off in here to the side. So that's where I'm at. We're going to take a break here real quickly. I want to show you the latest job on this mill, and then we'll show you a little bit more about the design of the mill. One of Chuck's subscribers saw my earlier build of one of the commemorative engines from the Gears engine show in Portland, Oregon, and he says, hey, I've got one of the casting sets left over. And so here it is. This is the engine. It is roughly 90% done. Most of the parts are machined. There needs to be some detailed work. Looks a lot like a V-twin, would you say, maybe roughly based on a Harley engine. The literature, the drawings that came with it suggested, well, you could put fins in this thing. And I thought, well, that's a great idea. So I set the horizontal mill up, and this is the head, goes here, and it's got fins. And currently, one of the cylinders is on the lathe, getting ready to have fins turned in this area. Not done yet. And a friend of mine says, well, if it's got fins, then it's an internal combustion engine. I go, okay. And he says, it should have a spark plug. And I go, no, steam engines don't have spark plugs. And so we went round and round on that. And let's look at what it's got. It's got a hole for a spark plug. It's going to get a spark plug, probably no wire. But this was a nice, fun project. I had to calculate exactly where each cut was so that the location of the cut left fins of equal width. And of course, this wasn't exactly a fractional dimension, and so there's some interesting adjustments to get the finning all turned out. But here's the cover for it, and the push rods. Got a nice little flywheel. There's a cam buried inside there. I've got I'm working on adjusting the length of the push rods, and I'm really thinking about taking these out and putting adjustable push rods in. Make that job just a little bit easier. So another week or so, probably ought to see this thing done. I'm going to take you on just a little tour of the backside of the mill, just for fun, because we have a little bit of time, and I'll show you a little bit more about this neat little machine. Okay. Well, just for giggles and grins, we're going to show you a little bit more about this horizontal mill. This is a 3-horse US-made motor, and somebody went to the trouble of replacing the original. I looked at this at one time at the idea of remotoring it, and I says, that's a tough job, getting in there and unbolting that and getting it out and getting another one in. So it's not going to happen. Now, the drive is taken from the motor with a set of 3 A-sized belts up to this shaft. And, oops, Chuck's panning up. So we have a V-belt drive to this shaft. Between this shaft and this shaft, inside the body of the mill, there is a ranging gearbox, high range, low range, and a neutral position. And then the output, this is the input shaft, this is the output shaft of that gearbox. On this is basically just excuse me. This is the output shaft. It drives a gear set that are pickoff gears. In other words, these can just simply slide out like that. You can turn the gears over. You're going to reverse them. Here is the other gear set. So there are 2 ratios available here, 2 ratios available here. 2 times 2 is 4. There are 2 ratios available in the gearbox. So this is an 8-speed mill. And offhand, I don't have the high and low speeds. At one time, I remembered what the gearbox ratio was, and I've even forgotten that. So I'd have to sit here and do some work to figure out the available spindle speeds. I need to have that information, but I don't have it right now. So, as I said, remotoring is a possibility if I thought that the spindle bearings would take it. But no, that's a terrible job getting that motor out, and I don't think that I would want to do that. Anyway, there's a little bit more information on how this mill was done. Very interesting design. There is no thrust on spur gears, and so this collar right here, or flange, simply rides on on bearings that are just part of the cast iron door. When this closes, the gearings are held in place. When you want to change speeds, open the door, just slide the gears off, put the gears on you want. Now you've changed speeds. So it's a very, very nice design. Simplifies the gearbox. A little bit more work than just moving a couple of handles, but for a small mill, it's ideal. Yeah, as Chuck and I were turning the camera off and closing everything, Chuck says, "Hey, well, let's look at that spindle bearing a little closer." In Screwy Tuesday number 23, we built this spindle up. We put the bearings in, we put the spindle in, adjusted the bearing clearances, and just to show you again, the spindle journal is cylindrical. Of course, then the bore of the bearing is cylindrical, but the OD of the bearing is tapered, and there is a nut on both ends of the bearing, and as this nut is tightened, it would tend to draw the bearing this way in the body of the mill, which forces it into its taper, and that decreases the clearance. And so one of the jobs when you put this thing together is to set the clearance. I do it with what they call a spindle lift. You mount an indicator on here and you lift. You see how much play is in it, and then when you get it down to what you think is about right, and I think I have about 1,000ths clearance. I remember 7 or 8 tenths, something like that. Then you run the spindle unloaded at speed for approximately an hour, and you use your little infrared temperature gauge and see how much the temperature rises. You want this to be just no hotter than you can hold your hand on it. And so this has passed the test. It has also passed the test of cutting. I have cut using a 4-flute carbide face mill, cutting cast iron, and there's no chatter. Cuts very smoothly. So I think that this spindle is pretty well adjusted.
How's that lubricated?
Oh, Chuck says lubrication. Yeah, let's show you about that. We're going to move the camera around here, and I'll show you a little bit about the lubrication. I can't show you a lot, but
you think we're good? Go ahead.
Yeah, Chuck says, what about spindle lubrication? I can't show you a lot because everything takes place inside here. But this is the spindle oil sump, and it's got a sight gauge, and it should have some oil in it. And I don't run a lot of oil in this, and I'll tell you why. The bearings are oiled by 2 3/8-inch square felt wicks that are laying in the bottom of the sump, and they go up through a passageway in the mill frame and enter the bearing at the bottom. And the wick goes up through the bearing until it touches the spindle. And then there's oil distribution grooves in it. So this is a total loss system. Any oil that you put in here continuously wicks up through the felt by capillary attraction, runs through the bearing, and falls through the frame. And this machine is an oil leaker. There's oil down in here. There's oil on the frame. When I got it, the coolant sump was full of lubricating oil because the shop that had this before was very good about oiling. They just weren't very good about cleaning. You know, so what if it got all filthy? But they kept the bearings oiled, and so they were in very good shape. But I only pump just a half a dozen squirts of oil in this thing whenever I run it, just enough that I know that the felt is able to pick up the oil, deliver it to the bearing, but not enough that when I shut it off, there's still oil in the sump, because all that oil is going to go down into the machine and down on the floor. So that's the way that the oiling is done. I have thought about, it'd be nice if I had wires sticking down through here. You could lift the felts up so that they weren't in the oil. But, you know, I'm not going to do that. I want to keep this as box stock as possible. And, yeah, you just live with the problems that it has. There we go.